really do want to thank you for joining us here at AIP and AIP Foundation for this evening's events. It is a thrill to see everybody in 3 dimensions, in person. So thank you. We've had to reschedule this event a couple of times, and thank you so much to the folks on the stage for accommodating the changes. And we also, as many of you will recognize, we had to do the launch of AIP Foundation in the fall of 2020 virtually, and not do the event that we were planning to have here at the time as well. But it is so great to see so many friends and so many supporters of AIP here tonight to engage in a conversation, which I think is going to be really thrilling, but engage in a conversation about our newest window on the cosmos, the James Webb Space Telescope. And it's, how fitting is it that we're here at the Cosmos Club to have this discussion, but not only because of the linkage there, obviously, between the Cosmos Club and the scientific community in this city and around this nation for a long time, but also you may or may not know that in about 2 weeks, on May 3rd, it'll be 91 years since the very first meeting of the Board of Governors of the American Institute of Physics was held at the Cosmos Club when it was located on Lafayette Square 91 years ago on May 3rd. And that is the date that we celebrate as the founding date of AIP. So it is very fitting that we're here at the Cosmos Club for that reason as well. So this is our first in-person donor event since we gathered at the Danish Embassy. Some of you may have been here when we were celebrating the purchase of a collection of 4,000 volumes, books, journals, and other treatises on the history of physics and astronomy going back to the 1500s that now forms the core of our rare book collection at the Niels Bohr Library and Archives. And it's also the first event, as I said, since we launched AIP Foundation in the fall of 2020. It's also the first event we've been able to hold since we were joined by Franz Cordova as inaugural chair of the Board of Trustees for AIP Foundation, and since we were joined by an amazing Board of Trustees that have been really pivotal and foundational to the success of AIP Foundation over the last couple of years. So I want to really thank Franz for being an incredibly impactful leader for AIP Foundation over the last couple of years, and also to the trustees that are here this evening. We've Vince Cerf, Nancy Greenspan, Charlie Bolden, Susan Avery, and John Mather as well. So really want to thank them for their leadership and their support. We're so pleased to be able to interact with our supporters and to help build our community of donors at AIP. We at AIP were committed to advancing the physical sciences for the benefit of humanity with a unifying voice of strength from diversity. And we execute on this mission by being what we like to term a vibrant federation of 10 member societies that in turn have 116,000 members across the physical sciences. And we're an institute for research and analysis and education that supports the full physical sciences enterprise. An AIP Foundation, who's hosting tonight's event, was established to support the Institute in its work by generating philanthropic support to deepen and share the history and importance of the physical sciences throughout the world, to motivate and encourage a new generation of scientists, to strengthen our commitment towards creating a more equitable and accessible physical sciences for all. That is the main principle and the rationale for why we've invested in the creation of AIP Foundation. And none of that would be possible without your support as donors and supporters for our work. So thank you. We thank the Foundation staff, the team, and the AIP Board of Directors for their support of AIP Foundation. And we really do, again, as I said, count on our supporters to really enhance our capacity to push out our mission and to push it forward in constantly evolving ways. The future for how AIP Foundation can support and really leverage the work at AIP is demonstrated by some recent news that some of you will be aware of, which is really, if you can allow me to be a little hyperbolic for a moment, which is really game-changing for AIP. So I want to acknowledge in particular Simon's Foundation and Simon's Foundation International for the most generous gift of $12.5 million over the next 5 years to help the work we are doing with our partner member societies, the work we are doing to roll back the persistent and egregious underrepresentation of African Americans in physics and astronomy. This gift from the Simons Foundation, Science Foundation International, will really provide us the means to effect real change that will impact the lived experience of Black students studying these fields. Fields that will supply the scientists that will work on many of the world's greatest astronomical facilities, such as the one we're here to celebrate this evening, as well as engaging in activity across every economic and scientific part of our nation's future. So to engage in the conversation about James Webb Space Telescope, I'm really delighted that we're joined by 3 of our trustees from the board of directors. John Mather, who's a Nobel physicist and senior project scientist for the James Webb Space Telescope. John is an avid supporter too of the Society of Physics Students. John has been involved with the telescope since its earliest days. My friend Charlie Bolden, who's the 12th administrator of the National Aeronautics and Space Administration, NASA. Charlie led NASA at a pivotal point for the telescope's development, as I'm sure we'll hear tonight, and its presence in the cosmos today is by no small means owing to his leadership of NASA at that time. And France, former director of NSF and former chief scientist of NASA, who's, as I mentioned, is chair of the board of trustees for the foundation. Her tenure at NASA coincided with the early days of the formulation of a concept of a large 10-meter class telescope to succeed Hubble that eventually became James Webb Space Telescope. I'm really thankful and delighted to welcome Miles O'Brien to steward our panel tonight. Miles and I have intersected a number of times in his work with NASA and my work with NASA, so it's great to see you here this evening, and thank you. Miles, as you probably all know, is an independent American broadcaster and news journalist specializing in science, technology, and aerospace, and he's been serving as the national science correspondent for PBS NewsHour since 2010. Miles, I turn the evening over to you, and thank you again for helping us steward this evening's conversation.
Yes, pleasure. It's a pleasure. Thank you. Thank you. So good to see you all. I feel smarter and richer just being in this room. It's just fabulous. So France Cordova, youngest person, first woman to be the chief scientist at NASA. Charlie Bolden, 100 sorties over Vietnam, 4 shuttle missions, 1 stint as NASA administrator. John Mather, cosmetologist, not cosmetologist. You know, if I had written that would have been better, but I actually just stumbled into that. But more importantly, he gave us the Big Bang Theory. So he's a TV producer too. So clearly I have a group of underachievers here, and I have to elevate this conversation for you. So by the way, happy 32nd birthday Hubble coming up in a week, 32 years. Let's go back for a moment. What are your Hubble memories? Charlie, wait, 32 years ago, we didn't even know yet about the spherical aberration. Do you remember where you were when you realized Hubble was not seeing straight?
I remember exactly where I was. I had, having been on the crew that deployed it, we were up in the stratosphere, and we heard, and all of a sudden our world crashed. And then Steve Hawley and I, because Steve had been the person who actually did the deploy with the RMS, and we instantly started reliving the deploy, because some of you will remember deploy day was a disaster. Nothing worked right. The robotic arm that was supposed to lift Hubble straight out didn't do that, and it started canting and rolling. And so I was reading angles to Steve, and Steve was moving one joint at a time instead of lifting it straight out. And I remember the day before we launched, we all went out to the payload changeout room, which is right on the pad itself, where before they close the shuttle doors, you can actually go in and look at the payload. And I remember taking my fist and I put it in, and the distance between the side of Hubble and the Longeron, the side of the space shuttle, I could just get my fist in there on both sides. So I knew how tight it was. And Steve and I immediately started going, what did we do wrong and what did we hit? And we started looking at film and everything, and we assured ourselves that we didn't cause any damage.
This is the astronaut's prayer, right? Dear Lord, please don't let me be the one to have done this up, right?
So I remember exactly where I was.
France, where were you when Hubble was launched and found out to be nearsighted?
Yeah, I was at Penn State University, and I was on a committee, a users committee for the Space Science Telescope Institute in Baltimore. And it was just devastating news, but we got to work immediately, all the different groups and committees, on how to fix the telescope. And everybody believed it was possible, and there were just some ingenious technical people on this group, and they came up with this optical jukebox solution. And it just, it was incredible. And then a couple years later, I was hired by Dan Bolden, then NASA administrator, to be his chief scientist. And so that was right before, just a couple of months before it was launched, the rescue mission for it, to put in the new optics. And so everybody was just going over everything again and again. Was this going to work? And people just, just shows the brilliance of the science community that they figured out a solution for this, and it worked.
That was an amazing mission. I think, in many respects, the space program was kind of on the line during that mission. John, here we are 32 years later. You're probably the only person on this panel who could really have envisioned what Hubble might have seen over 32 years. Could you have predicted all of what Hubble has brought to us?
No, absolutely not. The people that built it didn't predict it. People that said they predicted it got it wrong. And similarly, even we had just before that launched the Cosmic Background Explorer, and we didn't predict anything that we would see either, or how important it would turn out to be. So nobody knew there was so much treasure hanging out there, just barely in reach. Nobody knew.
They talked about it a lot at the cosmetology convention.
All right, so let's move into Webb mode here for a moment. John Grunsfeld told me that the James Webb can go where no Hubble has gone, and which is good. But John, first of all, bring us up to date right now on what's going on with Webb. You have got to be a little more relaxed than when I last spoke with you in advance of the launch. And I believe, was it 400 single-point failures or something to that effect along the way?
The number is large enough that I just stopped counting.
Right. So, but now we're at a point where things are looking very promising. Bring us up to date on where things are.
Yeah, so we launched it perfectly. The orbit was exactly right according to what we asked for, which meant right away we had about twice as much mission lifetime as we had required ourselves to have. So we were thrilled with that. That happened like immediately. And the solar panels folded out within minutes after the rocket let go. So that's all good news. And then it took us about 2 weeks to get everything unfolded. That all worked perfectly. Nobody had to go to the backup plan, not once. And we were thrilled with that. And so we're beginning to think maybe our good luck might hold. Where we stand now is it's all unfolded. It's all focused. The fourth instrument, the last one, has been cooled down to its operating temperature. It's about 6.5 degrees Kelvin, 6.5 degrees above absolute zero. And the refrigerator was a little worrisome because we had a little, I don't know how many people heard, we got a little accident at the launch site, and a mechanical hit occurred. We were afraid something might have been damaged, and the compressor for the refrigerator might have been, but it wasn't. So anyway, we kept our fingers crossed about all the things that were not under our control. And now we're thrilled because it's focused, pictures are perfect, and it's as sensitive as we said. It is so sensitive that if you were a bumblebee, a square centimeter gray object at the distance of the moon from the Earth, away from the telescope, we could find you.
So, and if you do find a bumblebee, that will be news, right?
It would be cosmetologic.
I'm going to need a little rouge. Actually, maybe I don't need the rouge. All right, so how nervous was the team? How relaxed are they now? I mean, give us a sense of what you've been through since the launch on Christmas. It really was kind of a tense time with very few options. You're not going to send John Grunsfeld up there, right?
Well, that's in a way that makes us less tense. I was just sure I'd done everything I could do. I was sure that all my engineering head buddies had done everything that they should do or could do. Scientists did not argue that something should have been done that wasn't done. We just thought we'd done the best we all can. And so I was just sitting there, oh, of course it's going to work. And a lot of other people were like that, and other people said, what is it? It's my part that fails. And so, but we've been all very fortunate because our part didn't fail.
So let's talk briefly about this first image we've seen on this rather unexceptional star as it's been described, but rather exceptional picture, 12.9 billion years back. But the star is interesting, but I think what's got most people really interested is the background. It reminds me of the deep field images, the first deep field images, which are long time exposures in Hubble in a piece of the universe that was supposedly dark, and it's filled with galaxies. And here you have this kind of same effect on this first shot. What does that tell you about what is in store here?
There's lots of treasure out there. So the telescope is what we said it would be, and we aimed it for particular reasons. We said, well, we think we know what happened, so we know how big the telescope has to be. We know how cold it has to be. We know how perfect it has to be. We know what wavelengths it has to look at. And when we see the picture, we say, that was about right. We built the right thing to look with, but we're still going to get surprises because that's the whole point.
So with that near infrared capability, how far back in time are we going?
We depend on what nature gave us to see. But we think the first objects could have formed within 100 or 200 million years of the Big Bang. So it's 13.8 billion light years from here to there. So coming real close as you can imagine.
How close do you think we can get?
100 or 200 million years of the...
That's it, and then it's just too opaque.
Then it's not that it's opaque, there's just nothing to look at.
Oh.
Because the galaxies didn't grow yet. That's one of the big mysteries. How did the galaxies grow? So we have the even earlier baby picture of the universe because we got the cosmic background maps that show hot and cold spots. And we say, well, there's no stars and galaxies in that. What happened then? So gravity supposedly acted on those spots and made them grow into things that we see. So we'd like to see the process happening. So that's one of the great objectives, one of many great objectives of the observatory, see the first things growing. But now it's a big question, well, what were they? We'll tell you later.
So there's the tease for you. So, France, you were there at the beginning when this was still being discussed. We called it the Next Generation Telescope for a long time. What were the conversations? What were the initial ideas as you recall them?
Well, Riccardo Giacconi, who another Nobel Prize winner for really starting X-ray astronomy, but at that time he was the head of the Space Telescope Science Institute. That was in just before 1980, and he was always looking ahead at the next thing. And the Hubble hadn't even been launched yet, and he was talking about we've got to get to work, and now we've got Hubble all ready to be launched in the next couple of years. So what's going to be the next big thing? What do we need to know? And so he got people really excited, and he charged his group, Pete Stockman, Illingsworth, and just a number of them who were at the Space Telescope at the time, to really think about and develop a concept. And they did that. And it started out really big, like something like 10 meters big. And then there was the Hubble launch, and there were a lot of other things going on, and the budgets didn't look so good. So then it became 4 meters. And then Dan Golden, when he was administrator, he said, so that was like the early 1980s on for a decade. He said, 4 meters is now, it's got to be 6 meters, and it's got to go way out there to the second Lagrangian point and so on. So there was just a lot of excitement, a lot of committees making it bigger, making it smaller, trying to figure out exactly what this was going to look like.
So you've had a lot of experience with big science projects. Mm-hmm. It's hard to keep them going, isn't it? There's a lot of money involved. A lot of people have their fingers in the pie. Congress gets involved. And it's difficult sometimes to sell science to the American public. Why do you think this idea survived?
Well, I think the last point that you mentioned, selling science to the American public, is never a problem. That's not it's that the projects take a long, long time to develop. And there were so many technical challenges with that. And a number of other projects that I've been privileged to be around, like the Laser Interferometer Gravitational Wave Observatory, that also took 4 decades to really reap a success. And so you have to count on Congress, which has annual budgets, to sustain a budget and keep paying for something that they've seen no return on at all. And just believe in the science and the scientists, and then administrators come and
Come and go.
They do, and they're all fighting for it. But and Charlie knows so much about this as well. But in NSF, which does big ground-based telescopes, and NASA, which does space-based telescope, there have been a lot of times for all of these big projects when we've thought, this thing is within a hair's breadth of being canceled.
Right.
And that was certainly the case for this telescope as well.
Now, Charlie, your first stint in Washington was right around this time, wasn't it?
It was, and it was the worst thing I ever did.
And this is a man who was shot at over Vietnam. So really, all right, welcome to Washington, right? So
That was exactly right.
yeah. So what was unfortunate about it at that time, and what are your recollections about at that time Next Generation Telescope?
Well, I came about the same time that Franz did. Dan caught me being rolled off on the gurney from my first command on the shuttle. I had been the commander for STS-45, NASA's first mission to planet Earth. And it was Dan's second day on the job. We had gotten word on orbit on April 1st that we had a new administrator.
How appropriate, April 1st.
And we went, nice joke. So what's really happening? And they said, this is not a joke. We have a new NASA administrator, and Dan had replaced Admiral Dick Truly. And we landed the next day, and there was Dan leaning over me saying, I want you to come to Washington to work for me. And I didn't have a clue who he was, and I used an expletive to ask him who was he. And George Abbey was standing behind me, and he went, but things worked out. He asked me to come have dinner one night, and I came, and I ended up at NASA as the assistant deputy administrator for a year. And we saw a lot of what Dan was an idea guy, incredible visionary. Yeah. And we saw him, as Fran said, kind of explain to people, we've got to ask for this because we want big telescope. We want a good telescope. With the Mars rovers, he was the person who demanded that we have 2, not just 1 when we launched Opportunity and Spirit. Because otherwise, who knows what would have happened had we not done that. But we kind of watched that develop and watched his ability to go really torque Congress off at times, but convince them that the programs that we needed were good. The other thing that helped us was everybody, even in Congress, understands to a certain extent and believes in decadal surveys. Mm-hmm. And so James Webb, when it moved up to #1 on the decadal survey, we knew that we were part the way there.
Right.
It's interesting. So it's kind of like the transportation bill. It takes away a little bit of the politics in a way.
It does.
It's in the survey.
You can't.
We have
they
to
can argue
with
They can argue with the administrator. They can argue with the chief scientist. Yeah. They can argue with anybody. But when you have a group of learned people who come from the national academies, and they have spent years developing this 10-year plan for one particular area of science that they want NASA and NSF and others to do, it's kind of hard to argue with it. OMB tries, but that's OMB.
Yeah,
we
that's
need
what they
to
do.
give a lot of credit to John Bacall, who led the 1990 decadal survey.
Yeah.
In the 1980 survey, it didn't really make it. It was introduced, but it just wasn't developed enough. But by 1990, and he was a really luminous scientist, and he brought it home.
Well, when I think of Dan Golden, I do think of, better, faster, cheaper. And we used to always say, pick two, right? And John, in that context, was it challenging to imagine a next generation telescope?
Well, actually, no. As long as the boss says we're going to do it, then we're going to do it. And there's a story there because with the committee that wrote the little book that said HST and beyond, this is what we should do after Hubble. It was a brilliant committee. They wrote a wonderful report, and Alan Dressler was the chair, and he went to meet Dan, and they hit it off. And a couple of months later, Dan gave an invited talk to the Astronomical Society. He said, "You asked for too small a telescope. We're going to build it, and it's going to be bigger." He got a standing ovation. So, right after that, everybody wanted to work on this idea, even though we didn't know what it was. So we're going to build it. So, okay.
So better, faster, cheaper, and bigger.
Yeah, well, he didn't talk about better, faster, and cheaper so much at that point. But he did ask us to say, find a way to do it for $500 million. Well, everybody that I knew said that's impossible, but we're going to, the boss, okay, we'll try, boss. So we did actually persuade ourselves, at least for a while, that we could.
Well, let's talk about some of the innovations that had to go into this. You have this idea, but a lot of things had to be invented to make this happen.
Eventually we had a list of 10 things we had to invent, but the biggest first one was how are you going to make sure it is in focus after you launch it, because we just launched one that isn't. And so, okay, number one, focus. And then number two is if it's going to be bigger, well, how is it going to be bigger? It's going to be bigger than the rocket. So Dan Golden knew that we'd already been working on segmented telescopes in classified work, because he came to NASA from TRW, which was working on it. He said it was possible. Okay, if John says he wants it, then let's do it. So it wasn't too hard to say, okay, we'll build you a bigger one. Then all the other things follow. Okay, you've got to invent the way to focus it after launch. The hexagons have to be on motors so they can do this. And you have to translate the math that we've developed to fix the Hubble into what we're going to do on purpose with the Webb. It wasn't the Webb yet. And then the detectors had to be better. We had to unfold a sunshade, as big as a tennis court, as it turns out. And it went on and on and on with just the 10 things that had to be proven. You couldn't even finish the design until you could do that. So,
when you think about all those things, and you're doing something that obviously has never been done before, how do you even begin to budget? And is that fundamentally part of the problem? You have to put a number on it, but you really don't have any idea.
Yeah. You really don't have any idea.
That's pretty much it in a nutshell. So maybe you should just, whatever number you come up with, just add a zero, and
Well, we have more experience now, which says that we do have some basic rules of thumb about how, if you're this far along in your project, then you should multiply it by a big factor, and if you're farther along, a smaller factor. But we were so early in the project that nobody had really settled. So we were just wrong.
So, Charlie, your second stint in Washington as the administrator, one of the early fires burning at NASA was right around the Webb Space Telescope at that time. By that time, Webb. What was going on at that time, and what was your mission at that point? I assume you were doing everything you could to save it.
I thought I was already handling the largest issue that I was going to confront as the NASA administrator, because my first budget, we had announced that we were going to terminate the Constellation program, which was the human exploration system to send humans back to the moon and on to Mars, and we were having trouble with it from both a performance and a cost perspective. So that was what we were really focused on, and trying to carry out the president's agenda of introducing commercial launch capability. And then all of a sudden, in walks, I forget who it was one day, and said, "We've got a problem." And I said, "Right? I think we're already working on them." They said, "No, we have a real problem, and that's with James Webb." And I said, "What's the problem?" They said, "Can't launch it in 2014, and definitely can't launch it for $5 billion. And I said, "I don't believe it." And so I asked John Cassani, or I didn't do it, but I tasked somebody to find a good leader for a comprehensive review team, and that became John Cassani and his team, and they spent about a year actually studying everything in gory detail and came back in and they gave us two choices. If you want to try to launch in 2014, it's going to take this much money. If you want to only spend this much more, then we've got to slip the launch. And then Franz brought out a point. You've got to have a champion if you're going to do this with money. And that champion has to be in Congress. And so I called Wes Bush, the CEO of Northrop Grumman, who was responsible for building it. And I said, we've got a problem and we need to go talk to Senator Mikulski after I go talk to the president. And so we had to go brief, I don't think we physically briefed the president, but we briefed OMB and everybody else. And then we struck off to the Hill to talk to Senator Mikulski. And just as she had been a champion for Hubble, she turned out to be a really tough champion because she had, you talked about my military stuff. She had Wes and me standing tall at attention in front of her. And she listened to our presentation. And afterwards she said, okay, I tell you what, we're gonna do this one time. And if you come back and darken my door, as much as I love JWST, it's done. So you gotta make it right. And we sent John Cassani back and said, hey, you gotta go back one more time and make sure we're giving her the right numbers. And that's where we came up with the, back then, 2018 launch for $8.5 billion, which was $3 billion more than we were priced at that time. And she kind of gulped and she said, well, let me go talk to Richard. And Richard was Richard Shelby, who was the ranking member at the time, and they were like brother and sister, and they didn't do anything. This is the way Congress used to work. They didn't do anything without each other, and the two of them, took it to committee and came out and said, go do it.
Wow, what a great advocate.
I tell people all the time, if you want to identify a single individual, now you can't identify a single individual for anything, but if you want to identify a single individual without which Hubble and JWST would not be what they are today, that single individual, because it's money, is Barbara Mikulski.
Yeah.
Wow.
And we invited her, we were trying to invite her
Would have been nice to have
be
her
with us
yeah,
tonight.
well,
and
we're thinking of her for sure.
Yeah.
But go ahead, France.
Oh, I was just going to add, and Chandra and Cassini before that. That was when I was at NASA as chief scientist. Those were, they just didn't know how they'd have enough money to send both of them up. And she asked me, in front of, in testimony in front of Congress, she said, choose one, Dr. Cordova. Is it going to be ACSAF, it was called at the time, ACSAF or Cassini? And I was just terrified, and so, how are you going to choose?
Split the baby.
It's like it's like a Sophie's Choice moment.
In the end, she got Congress to approve both of them. So.
Well, so it makes you wonder a little bit how things would go down today if you had to have that same conversation.
You probably, it's all conjecture. So let's be like I am. I'm the eternal optimist. Let's assume that if we had the same thing happen today, we'd find a champion. That's the assumption I will continue to work with until we find otherwise. Because if you remember, NASA has only been plussed up in this environment each year, and we've now gone through Obama, Trump. My wife says, don't say the name, but Obama 45 and now another president. And NASA's programs have gone relatively uninterrupted to include the very controversial programs. And it's been because Congress, has decided with Jim Bridenstine that we should support this. And now with Bill Nelson, we should support this. So I remain the eternal optimist. And I think when we go in with the next thing after James Webb, which will come, it's got to come, we'll find support.
Yeah, and it's interesting to me, and I was talking with people before this, that that Congress really is visionary. When you present a great scientific case and they've made an investment in it, you're going to find a lot of supporters that are not going to let it go down. they are really motivated by the science, which I feel very encouraging, more so than the budget. They'll
They actually
find a
buy
way to do it.
they buy our story that NASA is nonpartisan, and it gives them at least one out, to do the job of governing. And I'm incredibly proud to be associated with an organization that does that. And you look at everything that the agency does, it is the only soft power tool right now that's able to continue to do things in the midst of an incredibly difficult diplomatic time when you talk about Russia. And it's almost as if nothing's going on when you look at what we're managing to do with the International Space Station. So I'm not sure how long that will survive.
Let's hope it
but
does.
for
But
now,
that's
yeah.
a tough one for sure. John, let's walk through what the big goals are. Let's not forget that.
Oh,
Oh, before we do that though, you mentioned what's next. I was going to save that for the end, but since you brought it up, what do you want to do next? The decadals have looked at this, right?
Yeah, well, okay, the big thing the decadal said for astronomers was, for NASA, please build us a telescope about the size of Webb, but much more perfect, so it's able to see little planets, little Earth-like planets orbiting stars like the sun. So that's like the hardest astronomy project we've ever had. And it could probably be done for a Webb telescope budget or maybe less, don't know. So they said, well, we don't know how to do it, but please figure it out. So that's the first one. And they also have two other great observatories for X-rays and for far infrared astronomy that would follow. They want them too. So this is really a 50-year project that they've given us to do. And as long as things keep on working, we've got plenty in front of us, and they will all be brilliant and do astonishing discoveries.
And when we talk about technology, the thing that is beginning to loom is, I believe, you don't have to build a big telescope and launch it on a big rocket. We can build it in space. It'll start in some of our lifetime. We have an experiment on the International Space Station right now that the Axiom crew just took up, looking at a different type of lens that can be formed when you get to orbit, and then you build a telescope from that. So these kinds of things we need to remember. Technology is not standing still. We're looking at things that are mind-boggling when you stop and think about it. But everything on JWST, as John said, was mind-boggling. How do you focus these doggone segments when you're now talking about almost absolute zero, and we don't have anything that's that rigid? So we invented these beryllium backplanes or whatever it is that the drives are mounted to with a coefficient of expansion and contraction or something. Now I'm out of my league here, but it's like zero. So that when you screw on it, it sits there like it's down here on Earth. We didn't know how to do that before JWST.
Yeah, and we invested a fortune to make that.
That's absolutely right, yeah.
So walk us through the big four.
The big four.
The four main things
Yeah.
you're after here.
Well, we've already talked about how did it all start. What were the first things that grew from the Big Bang material? Black holes, galaxies, the first stars. And we got a story which may or may not be true because there's some big mysteries out there. There's dark matter and the dark energy. Nobody has a clue what they really are. And we don't even know if you ever could find out, because nature might not cooperate with our wish. So anyway, what was the first thing? And then how did the galaxies grow? Well, the Milky Way, it's now this wonderful, big, beautiful pinwheel. Well, how did that happen? Well, probably maybe 1,000 little pieces were pulled together, like the Magellanic Clouds that you still have nearby. They and others fell in, and so somehow we ended up with this big pinwheel. But they aren't all like that, so there's a lot to learn about the growth of galaxies, and especially the conditions that make stars grow. So stars grow from the debris of other stars. So you see these beautiful pictures we show you with the glowing clouds of gas and dust, and the Orion Nebula, the middle star in the Sword of Orion, is one of these places, the Eagle Nebula. So we look at these things and we say, oh, I know there's a star growing in there because they keep popping out. And we can see them with the infrared, but all we see is there's a big glow. So how did that happen? We'd like to see the planets and the stars growing today because they're still happening. So that's number 3. And And then the fourth one, of course, is planets themselves, close up, the ones in our solar system and around other stars. And especially, are there any that at all like Earth? So that's a really hard problem, but that's sort of top priority. Everybody wants us to do that one, even though we didn't start off to do that.
So we don't talk so much about the spectrograph capability. Tell us about what that would be.
Well, a spectrograph is something that spreads out the light of a star or a galaxy into the colors, onto a rainbow. And so why do you care? Well, to an astronomer, one of those is worth 1,000 pictures. And why is because it tells you what's going on inside an object. How hot is it? What's the chemistry? How is it moving? And maybe if you can figure this out enough, tell the history of it even. So you look at the sun, you say, what's a nice big hot thing? Spread it out into the spectrum, you say, all the chemical elements of the universe are up there, including helium, which was discovered in the sun because of that. So anyway, there's an awful lot to get from a spectrum. And we'll never get it on the front page. But we astronomers love them.
Well, speaking of the front page, how many textbooks have the Eagle Nebula on the front of it, right? It's an iconic image, to say the least. The infrared version of the Eagle Nebula doesn't have the wispy clouds, which, of course, is in the way if you're a scientist.
Yeah.
Will these images be as iconic as Hubble and engage the public in the same way, do you think?
Oh, I certainly hope so. That's the plan, the wish, and we're doing everything to make it happen. But now, okay, nature, what did you do? So we don't control what Mother Nature gave us to see. So it'll be a bit of a surprise.
So what will the first images be of? I mean, we're getting into that phase now where they're going to start aiming the camera.
Yeah, honestly, I do not know.
Is that need-to-know basis kind of stuff? Is that it, right?
A little bit.
Yeah.
But,
They'd have to kill you, that kind of
no,
stuff?
it's more like we want it to be a surprise for everyone. And we don't want people with some other telescope to say, well, I got a better picture than that. That happened, with the Hubble. People said, I've got a bigger telescope than that. So as soon as they got wind of what we were going to take pictures of, they started trying their own. So anyway, but we also know that nobody can compete with the Webb because you just can't do it.
I think you're going to be okay.
It's so different from anything you could do with any other telescope. It doesn't really have competition.
So when are we going to see these images? This summer?
Yep. The original plan said finish the setup by the end of 6 months, which would come out to be June 25th or something. So somewhere right around there, we should have pictures. And it'll take us a little while to make them ready to show you. But
now, Webb is not a successor to Hubble. Hubble obviously is still in business. It's meant to complement. And I do know that it's important from a scientific perspective to have, when you have observatories operating in synchronicity, that's a really good thing. This armada of telescopes we have in space and on Earth, able to check each other out and check their data out is a very powerful tool, isn't it?
yeah, basically, I saw something. You see it? Did you see it? Did you see it? And that happened with the LIGO that we were talking about earlier. When people saw a gravitational wave, it turned out to be coming from 2 neutron stars that had mushed themselves together and made this huge thing. Well, 4,000 astronomers around the world wrote papers about that. And every telescope that could possibly look at it did. So, yeah, it pays to have more.
Yeah, I mean, LIGO is a good example of
Yeah.
multi-platform, isn't it?
Yeah.
Yeah.
Yeah. Well, there it's very important that you have more than one facility so that you're not fooling yourself and you know that the observation is real. So there's that, If it's going to shake the Earth, it has to shake the whole Earth, not just where you're standing. So.
Yeah. So Charlie, the decision on
I'm
Webb,
just sitting here amazed at all this brain in between you and me.
the cosmetologist, yeah. So, Charlie, I know astronauts loved Hubble because they got to go to it, and it was kind of a fun mission to do, and you having done one of those. I know there was some talk, at the end of the game, probably when you were in the corner office there, about giving it some kind of capability to service it. Tell me a little bit about that. I know John Grunsfeld.
Well, the
was a
big thing they
proponent
wanted
of
to
that.
do was put a grapple fixture on it. That's all they asked for, was just put a grapple fixture on it. as I learned when I left with Perseverance, when I said no helicopter because it won't work, no one probably listened to the administrator, but we will only know if we ever need to go and try to go do something robotically to JWST. I have no idea whether it has a grapple fixture on it or not.
No, there's no, I don't think it.
Just because the NASA administrator said don't do it doesn't necessarily mean it wasn't done.
You think they snuck one on?
That's why I'm looking at John.
But we did actually figure out how to do it if we have to.
Really?
Yeah, oh yeah. You can grab onto it the same way the rocket does. There's a big clamp ring that's quite large, and you just have to go up with a matching one and clamp right on. And we need a pattern on the end so the robotic camera can say, I know where I am.
Oh, you put a pattern on it too?
There's a pattern on it.
See what it's saying?
Yeah.
Yeah, see?
So
But they didn't do what I said don't do. They didn't put a grapple fixture.
yeah, we did not.
You need to stay in shape, Charlie. You might get this mission. You never know.
Well, and if we did our job right, we don't need to do this. By the time
true.
It's out of gas, then we'll be about ready to launch the new one,
So
whatever it is.
is there a scenario where, it's doing well? I mean, would you have predicted 32 years for Hubble? I don't know if anybody would. If it was doing well, would you go refuel it?
It's logically possible, but nobody figured out how yet.
Yeah. We got some time on that one, I guess, yeah.
Right now, we don't have the rocket to go, so we haven't had to solve the problem. But, well, somebody wants us to do that. I'm sure they do. And by the way, Congress was pretty worried about failures, so they made a policy, I don't know, 10 or more years ago that said, please study how to repair your telescopes in space, would you please? So there's a law that says we should do that. And for the Webb, it was hopeless because there was no way to get anything out there to L2. The Lagrange point where we put this is 1 million miles from here. No rocket can go there yet.
So if you don't repair the telescope, you're breaking the law, essentially.
No.
Who's going to arrest you?
Yeah. Not quite like that.
Well, let's talk about, we've talked about the first slide, we talked about the first images. What's going to be the first year? I mean, what's kind of intriguing about Webb is it's a wide open scientific process. Any of us in this room can submit a proposal. And who's going to be deciding on, who gets time on the telescope? And do you have any idea where it's going to be pointing?
Yeah, I don't remember where, but I can tell you the categories of what we've chosen. First, I'll tell you how we chose. There were several teams that built the instruments, and they all got dibs on some time. We said, okay, you instrument teams, you get half a year. That's a lot of time. So they specified all the things they wanted to look at because they thought it through and they've been working on it forever and ever, like 20 years. So, okay, they get to do that. Then we ran a competition for early release science. So, okay, these are teams that we're going to say, we're willing to work on this and give our heart to it, but we're still going to give all the data out immediately. So we chose 13 of those teams. And so then after those decisions had all been made, then we ran another competition. Okay, entire world, you write to us and tell us what you think is the coolest thing to do. And we got well over 1,000 proposals. And we chose about a quarter of them.
And this is just from anybody who had interest?
Yeah, of course. Most high schoolers couldn't write one, but about 10% of the selected proposals are run by graduate students, which is a great accomplishment from NASA. We did something called dual anonymous peer review, which is a cute thing. We said, we're not sure that the old guys are the best guys, but everybody thinks they are. So let's not do it that way. Let's make sure you write your proposal so we do not know who you are. We're just going to read the proposal and see if it's a good proposal. And so...
Who you are or what you are.
Who you are or what you are.
So it's just a proposal.
Just
completely
a proposal.
Double blind, whatever you want to call it.
It's anonymous. So we don't know who you are. And so it has changed the results a little bit. So the proportions of scientists that win match the proportions of scientists that propose. So
have there been a few surprises when it's revealed who wrote the papers?
I don't know if it's surprising at all, but I think perhaps the fact that the graduate students did so well as a group is surprising to me.
Frances, this is a great way to engage people in science, isn't it?
Yeah, absolutely. One of the I was thinking, what proposal would I really like to see done? And then I read about a female astronomer at UC Merced who proposed a dark matter experiment, and I happen to have a particular affection for dark matter experiments. So something I'd like us to nail before I leave the planet, is what is dark matter. And she's doing with 20 other people, she's the leader, but 20 other people around the world, this gravitational lensing of, the big globs of dark matter, imagine that, can't be visibly seen in light, would have enough gravitational mass that they would bend the light from quasars behind them, and then you would see the signature, the Einstein ring, or depending on exactly how it's located, you would see a signature of the same source imaged multiple times. That's a very difficult observation to make, but it would sort of nail if there were big globs of dark matter that had not turned into galaxies yet, let's say in the early universe. And so that would be one confirmation. So that was something that I read about. A few of the observations have been published in various things, and that was one that caught my eye.
So Webb is uniquely positioned, perhaps, to solve this dark matter riddle?
Well, it depends. As John was saying, there could be surprises.
Yeah. So we have struck out over and over and over and over in every laboratory experiment. Nobody's seen anything.
No.
Or at least nothing that's stood up. There have been a few things of claims that there was something there, and they all went away. So it could have been weakly interacting massive particles. They call them WIMPs. Well, then you have to imagine what would they do if you had one, and you try to look for that. Well, nothing turns up, and they've tried for years. And it's not like the dark matter is a surprise. We've known about it, at least had hints about it since 1930 something. Mm-hmm. Yeah. So, well, who asked for that? That can't be real. And then finally, it is real, but we still don't know what it is, and we don't even know if it's one thing. What if there are 2 or 3 or 5 different kinds? Well, how would you know? Anyway, all we can do right now is to see what does it do to light, and what does it do to other things.
Are you a little surprised we still don't know?
No, I'm not surprised. Who thought it was going to be easy?
I want an answer. I want my dark matter.
Yeah. Well, I do too. But persistence is required.
So what are your thoughts on being alive and an astronomer and somebody who loves science these days? I mean, we used to call it the golden era when Hubble was still is in its heyday. Of course, Webb is truly gold, but I mean, are we taking it to a whole nother level here?
Yeah, I think so.
Yeah.
You'll see.
Yeah.
And it's become so much more participatory, which I just love. I mean, there's so many ways you can contribute to science without necessarily being John Mather. But I mean, we've seen Congress, we've seen communicators of science, we've seen just so many engineers and people supporting the missions, on the ground, also trying to understand these big questions. What is dark matter? What is dark energy? What do exoplanets look like? And so on. And I think science has become so much more embracing of all kinds of careers that all go towards elevating science and putting it in the public consciousness. And so I think that's very hopeful for the future, that there'll still be that investment because there are so many people that are engaged in different aspects of it.
Well, I think if you find dark matter, you might have to make some room on your mantle for another Nobel, potentially, right? Is that possible?
Yeah, not a chance. It'll be made out of dark matter.
All right, we have some time for questions, and there are microphones in the room somewhere while we ponder dark matter. And I think Vint is going to do the first question. He's up front.
This is absolutely wonderful. Thank you all for taking the time to brief us on this. Except, John, we'd like you to tell us more secrets, but I understand why you didn't. I have a question about, people have talked about far side of the moon possibilities, whether it's radio telescopes or something else. Does that look like it's actually a worthwhile thing to consider?
Yeah. Okay, I'll have an opinion. Yes, I think so. We're not to where we have to have it yet, in the sense that we haven't done everything on the ground here on Earth that we could. But if we get to where we say there's still something out there and we can't do it from here and we really need to know, then the far side of the moon is actually a very special spot. It's the quietest place in the entire solar system for radio astronomy. Because the Earth is a source of radio, transmitters, radars. The sun, source of radio interference. So on the backside of the moon, when it's nighttime, it's dark, it's cold, it's quiet. So that's where you put your radio telescope, if you need to.
Or a nice hotel where you could get a good night's sleep.
That too, yes.
Maybe that's where the dark matter is. You know,
Yeah.
who knows?
Yeah.
Another question from this august crowd here. Anybody else have a question or a comment? Right over here. Yeah.
The biggest feature that we see is the sunshade, the so-called tennis court-sized sunshade. Why do we need a sunshade, and why do we need stuff to cool down the instruments? I hope it doesn't seem like these are obvious questions, but space is supposed to be very cold, so it seems like you wouldn't need to cool down the instruments. And also, we have lots of other sensitive instruments out there that don't have giant sunshades, so something special about the Webb. That's why I asked those questions. Thank you.
Yeah,
It's a great
It's a good
question.
question. I'm sorry we overlooked
did-
that.
we
That's
did-
an
we
important
should-
one. Yeah.
we should have said that at the
Yeah,
beginning.
we should have done that. So thank
wanna,
you.
Yeah, okay, well, we want to pick up infrared light. So why infrared? Because it tells you different things. You know, you've seen the infrared images of the cameras when you walk in front of it and you see your eyeballs. It just shows you a different aspect of the universe. And what's different? Well, the most distant universe that we can see comes up to us in the infrared because of the expansion of the universe. Things that are too cold to light up to where you can see them with your eye, they still transcend out infrared. And those beautiful dust clouds, they become transparent for infrared. So, okay, so now you know, that's the next opportunity for science. Now, how do you make a telescope like that? It's got to be colder than the things you're trying to see. So cool it down until it doesn't glow by itself. So that's why the big sunshade. Protect it from the sun.
But it's more than a sunshade. You have to have an actual cryo cooler as well. So we know that
one of the four instruments has its own sub-refrigerator, but if we didn't have that instrument, it would still have been cold enough for the other three. So cold. So you're right. If you just keep the sun off of something, it will cool off a lot.
7 Kelvin. That's pretty cold. That's for sure. Anybody else with a question or a comment?
And stuff does heat up.
Oh, here we have one over here.
Going back to your comment about space being cold, ask a spacewalk crew member that experiences a 500-degree temperature swing every orbit, because when they're in the sunlight, it's 250 degrees. When they're on the dark side of Earth, it's minus 250. So it's not cold all the time. It depends on whether sun's on you or not. The sun is amazing as a radiator, and the reason it took them so long to get the telescope to where we want it is because instruments don't cool down instantly. It's taken months. And if you allow the sun to hit the telescope, now you got to take months to cool it down again, and you don't want to do that. And that's the big purpose of the sunshade.
And John, if those instruments do rise in temperature, you really lose your ability to see deep into the cosmos.
Yeah,
right?
well, you don't want to melt anything either.
Yeah, well, that's
and you do have a giant magnifying glass out there.
Mm-hmm.
I have seen pieces of telescope that were melted by the sunshine.
Not good. Yes, sir.
In the last few years, I've seen astronomy has sort of evolved into looking at objects in space in many different ways at once, what's called multi-messenger. And I know that I've heard that the James Webb has to be calibrated against the Hubble, but what are the plans for teaming up with other telescopes? What are the ones that you most want to team up with to study objects? Or is that still secret?
It's not secret, but basically we made everybody write a proposal based on what they already know from all other telescopes. So in a sense, we're already teaming up with every existing telescope. Then we'll find something and then say, oh, look what I saw. And they go running back to all the telescopes that they have access to. Can you prove that? Are you sure you saw what you said? Okay, we're very argumentative.
The Vera Rubin telescope will come online in the next couple of years. That's a big ground-based telescope in Chile. And that's a unique telescope, and it's going to make all sorts of discoveries. And so those will be things that can be followed up on. And that's kind of the way it goes, is that you follow up on new discoveries with the telescope, and then you can really see what their capabilities are.
Yeah, give a few words about what Rubin's niche will be.
Well, it's timing. It's got very wide optics. It's going to see a large portion of the sky, and it's going to do continuous observations and keep on doing them. And so taking tremendous amount of data, looking at the temporal nature of the sky and looking for objects that go blink and pop off and have, I mean, the universe is so transient. It's not static at all. And so we'll be investigating stars that burst and have nova-like eruptions and that sort of thing. So I think, and it will also be doing some dark matter experiments and dark energy as well. So I think that it's really looked at as a survey telescope. It used to be called the Large Spectroscopic Survey Telescope, LSST, and then its name was changed by Congress to be the Vera Rubin Telescope. But it's just going to keep on surveying the whole sky that's visible to it over and over again and looking for these.
And near-Earth objects as well?
Well, that's a good question. I'm not sure exactly what its capabilities are there, but yeah, it will definitely be able to do some of that. In fact, yeah, the Defense Department has some concerns about that. Yeah.
Look up.
Yeah.
Up. All right, so question over there.
Yes. What, if any, capabilities from the previously proposed terrestrial planet finder were incorporated into the Webb, or are those capabilities supposed to be for the next telescope in line that you mentioned?
Could you hear it okay?
Yeah.
Okay.
So the
Everybody
question was
hear?
about what happened to the terrestrial planet finder
Right.
work that we did before, and what did we put into the Webb telescope about that. So Webb was designed without the expectation that there was going to be much to see. We didn't know there were planets around other stars when we started. Then one or two were discovered in around 1995, I guess. So, okay, what are we going to do? We've already set out what the basic idea of the telescope is. It's not a planet-finding telescope. But there are a few things we can do. We will watch when a planet goes in front of its star. And it's called a transit. So, okay, now you know there's a planet there. We can do more because some of the starlight will go through the atmosphere of the planet, if it has one, on its way to our telescope. So now your job is to figure that part out. This is not a very big amount, but figure that out, and maybe you can tell if there's a planet that has water in the atmosphere. Maybe even a little planet, sort of Earth-like planet. That would be really cool. So we didn't change the telescope much to make that possible, but because it would all happen too late.
Well, it's amazing how the exoplanet picture has changed in the course of this project, right?
Right.
Yeah, when I was a kid, people were quite sure that planets were extremely rare because we had no clue how they would ever have formed. And so obviously we are the only solar system in the entire universe. That was the wrong math. But now we know that they happen almost all the time. Almost all stars have planets. And now the question is, if they don't, why don't they?
One more in the back there, Marianne, and we'll come back to the front.
Yes, my question is, if
Hold the mic up close.
if inexpensive super heavy launch capability pans out in the near future, the Starship Super Heavy launcher, would that substantially affect where you would take telescope design, space telescope design?
Oh yeah.
Bigger diameter, right?
Yeah,
That's a key
bigger
thing.
makes it easier. The Webb telescope would fold very differently if the rocket were bigger. And it could have been heavier. We had to make things ultralight to get it up on the rocket that we could get. So everything would be different. Yeah. And I watched the movie of that starship. Oh, it just sort of looks like it knows what it's doing. Goes up and floats and lands on its tail, just like in the science fiction stories from
It's
50
got a
years
Buck
ago.
Rogers feel to it.
Yeah, it does.
Yeah,
So
it does.
maybe it actually will work.
Yeah. I got a question from Ben here again.
Just a quick.
No, hang on, we'll do Ben first. Then go ahead.
So here's the question. Recently, there have been a couple of coronal mass expulsions, and it just occurred to me to ask whether or not the James Webb Telescope is at any risk of a CME.
Oh, the CME is it's coronal mass ejection, so it's a blast of mass material from the sun, and so not as far as we know. We know they come occasionally. We have not noticed anything bad happening when the little ones come that we have or had already, and there's always the chance of a really big one. And so we designed knowing that they can happen and more or less how bad they could be. So keeping our fingers crossed that we did the right thing, but we know we know it's a big deal.
If you're an astronaut, you don't want to be in space during one of those, right? That'd be bad. That'd be big trouble.
So here's something that might surprise you. The trouble with them is not only the blast of material, but sparks. We've got this giant sunshade. It looks like a capacitor. You could store energy in it if the layers weren't all connected. So you have to make sure everything is electrically connected, that no part can have a different electrical potential than any other part. So we've spent a lot of time making sure of that.
Wow. Wow. We got to think of a lot of things
Interesting.
here.
Yeah.
Other spacecraft have been lost because of sparks.
That's a good detail. All right, go ahead.
I'm just curious, how far ahead have you booked the telescope? How long is your queue of projects?
1 year.
So get busy. You got time. I think the proposals are due at the end of the year. We got a question up in the front here.
in the front.
If you want to get it. The proposals due at the end of the year. Is that the idea for next year? Yeah.
Thanks. We've heard a lot tonight about a really big project and other rather large projects, but you are sitting on the stage, each of you, probably because you've benefited from other small projects that were nurseries for either you as an administrator, as an astronaut, as a scientist. And I was wondering if you could reflect on some of those smaller projects that enabled you to sit where you are today, that also need to be funded.
Well, I mean, as far as ground-based astronomy is concerned, there are telescopes all over the world. Those are all, different sizes. I spent my graduate student career and afterwards going to all sorts of exotic places to observe the heavens. And yeah, that was great. But at the same time, I also used a lot of space satellites because, like this gentleman was talking about what was then multi-wavelength astronomy. It was all in the electromagnetic spectrum. But you wanted to combine observations from space in one wavelength using an X-ray or gamma ray telescope with something on the ground. And so my generation was the first one because NASA opened up its facilities to anybody to apply. They weren't owned by a certain group or university. And so I think that that's when the transformation really started, that if you were raised in graduate school as an infrared astronomer or as an X-ray astronomer, and at Caltech where I was, we had both on the same floor, we figured out we could work together and we could observe the sky at both X-ray wavelengths from space and infrared wavelengths from the ground. And so that was really transformational.
Because I'm an earthling, the ones that are my favorites are those that are Earth observing. So you look at things like the Global Precipitation Measurement, the instrument that we did with Japan that enables us to measure the amount of water that falls back to Earth and how much evaporates. And we've got other instruments that now, because we know that sea level rise is critical, that allow us to look through the canopy of jungles and areas and actually tell what the elevation of Earth happens to be beneath the canopy, say in an area like the Amazon, and we were really off before we developed these smaller telescopes that actually can look through the canopy and tell us where the ground really is. So areas that we thought were okay, we were really measuring the canopy tops and not the ground where people live. So those are the ones that are my favorite.
Yeah, I'd like to say also something transformed scientists a lot lately, which is these things called CubeSats. I don't know, how many people have seen them? The smallest one is 4 inches square cube. It's a CubeSat. So you can make bigger ones combining small cubes. And when I first heard of them, that's useless. Astronomers need big telescopes. But it's not quite true. There are a lot of things you can think of that we could do and should do with little ones. And so suddenly any university with a wealthy parent can buy one. So a lot of people here could buy one. So that's pretty spectacular.
And John mentions the CubeSats. I think all of us love CubeSats because that has allowed kids in elementary school to become involved in astronomy and Earth observations. St. Thomas More is an elementary school down in Arlington. They were the first elementary school to build a CubeSat, build it in the school, send it to the International Space Station where we popped it out of the CubeSat deploy mechanism in the Japanese experiment module. And it's amazing how it gets kids interested, and there's probably some future Nobel laureate in that elementary school.
It's nice to have all that data on our favorite planet, Earth, right? And it really does. I was talking to a guy who runs a weather app, and he's launching his own CubeSats to get his own weather data. He's not going to bother with NOAA anymore. He has his own capability. Anybody, a question over here? Yeah.
I was going to say that the CubeSats were first planned at NSF, not at NASA. Sorry to put in this. I mean, one expects that it would be done at NASA, but it was at NSF that we first brought it up, and in our division. So I just wanted to put that in.
So you get to take credit, France, for that one.
Well, that and it's small science.
Yeah.
Generally, people think as NSF doing small science, and NASA doing big science. So I'm saying there's a great deal that you can do with the CubeSats.
Absolutely. Any other questions?
As well as
Oh,
graduate.
I'm sorry.
No, just also have a graduate student make it part of their thesis project or something like that. An individual science can be done with it.
And a lot of international, I've been to a lot of countries in Latin and South America where they just don't have the facilities we do, but they're building CubeSats and then getting partners elsewhere to launch them. I wanted to go back to this gentleman's question about the multi-wavelength astronomy. John, how flexible is the Webb telescope at pointing? If something is discovered, a supernova or some other big cosmological event, how flexible can it point?
Pretty flexible, but we're human operated. So it takes us a while. You call us up, call the director and say, I got this really important thing. Can you point the telescope over there? Well, number one, prove it to me that it's important.
Yeah.
And number two, okay, we'll do it. Now we have to get the people to decide what to do. I have to stop whatever it was we were doing and now send a new set of commands to do this. And then we have to get our turn with the Deep Space Network to send the command up. So it takes of order at least a day, probably 2 days to go through this process. So we're not able to answer supernova immediately, although people would like us to. And the telescope could go quickly if we just happened to be lucky and everything was connected at the right minute, but we won't usually.
But I imagine it doesn't have a very wide field of view.
No, you have to know exactly where to look to see anything.
Yeah.
And it takes about an hour for it to go from there to there.
Right.
Looking at one thing to another. But we certainly plan that something is going to be important, and we expect to get many calls every year. Look what I found with the Rubin telescope. The Rubin telescope is telling us that we get 10 million things that changed every night.
Yes.
So some of them are going to be important.
So is this going to be a published phone line that anybody can call?
I'm sure it is, actually.
You get some great calls when you do that.
Yeah.
Any other questions from the audience? Yeah, in the back there. Can we get a microphone there? Oh, you got it. I'm sorry, I didn't even see you there.
I do
Go
have
ahead,
one.
Mike.
So much in astronomy is based upon knowing how far away things really are. And as I've followed this through the years, there's the chain, the parallax, and the variables, and the supernovas, and so on to figure this out. What I wonder, number one, is how confident are we really in all of that? And number two, will the Webb telescope give us any independent insight into that?
Yes, of course we're confident.
Oh, I'm sorry, I didn't.
Confident, and often wrong. Astronomers were very confident for half a century that they knew the rate of expansion and the distance scale, and there were two camps, and one of them was twice the number of the other. Now we've been working at it for a long time, and now we've got two camps, and they're about 10% apart. And we do not know why.
Yeah.
So it's a fascinating topic. And yes, of course, the Webb will be working on that topic too, but don't expect a quick answer because we've already worked really hard on it, and we cannot figure out what's the matter.
It should be able to see supernovae much farther away and that are redshifted and all. And so just doing the dark energy problem will be, I mean, it'll just blow that wide open.
Yeah.
I think.
So we'll have our special in different ways, but to get really super accurate, you have to work really hard. And so we build the telescope and it's not good enough yet. You have to figure out how to use it.
Is there a question over here? Yeah, go ahead.
Yeah, John, you talked about how we're going to be able to see within 100 to 200 million years of the Big Bang. What are the technological advances we need to get all the way to the Big Bang?
Oh, as far as we know, it's impossible. Well, what nature has given us objects to look at with telescopes, and we think we've got something that's good enough to see them, almost the very first ones. Now, there are not very many of them to find, so we have to have some good luck, and we have to have all this wide field search telescopes like the Rubin telescope that can look at the whole sky, and the Spitzer space I lost my brain here for a minute. The next telescope we're sending up after Webb is a wide...
The Nancy Roman.
Nancy Grace Roman telescope. The wide field telescope will search the sky for rare things that are important to us. So then we'll follow up all of those things and maybe we'll find out the answer to your question. But anyway, yeah.
Anything else from the audience? One more over there. And we can pass the microphone in that direction. Yeah, raise your hand. There you go.
So kind of building off that question, say we had the technology to look back to the Big Bang, like that period, what would be the next frontier beyond that? Because that's the big push, is to look back to the time of the Big Bang, see how things were created. So what would be the next frontier if we were able to accomplish that?
Yeah, okay, well, if people want to know, was there something before the Big Bang, and we haven't a clue. Or maybe I should say we have too many clues and not enough way to tell.
But there are other kinds of telescopes that look at, going back to this gentleman's remark, at other phenomenon like gravitational waves, like the LISA gravitational wave observatory that would be up in space and would have a tremendous baseline, very widely separated detectors that could really deduce things about the Big Bang. They've been looking for signatures that really verify what we think happened and so forth. So we've been talking about an imaging telescope that operates in the electromagnetic spectrum, but there are other telescopes. There are neutrino detectors on the ground. There are these laser interferometers up in space on the ground that could really, really push our understanding of what happened at the Big Bang. much better. I do have a question for John that I have to ask him. I want to know, as a little boy, how did you grow up to ask? You've been involved in some of the most amazing. I remember when you showed the cosmic X-ray background, not the cosmic background experiment, Kobe. And everybody at the AAS meeting, their heart stopped for an instant. It was so amazing. And now this telescope and so many other things. So what is it that you wanted to be when you grew up? And
Oh, golly. I didn't keep a lab notebook, so I can't really tell. But I can sort of remember some things. When I was about 6, my dad told me at bedtime, your body is made out of tiny cells and there are chromosomes in there and they govern your fate. Oh, wow, that's interesting. I'm interested. Tell me more. So about 8 years old, we go down to the Museum of Natural History in New York, and I see the planetarium show and the bones and the volcano stories, and I want to know more about this. And there's this giant rock, the huge meteorite that sits near the planetarium. Where did that come from? And so I got started. I read in everything I could read. So another part is my dad's a scientist, studied dairy cows. My mother's dad was a bacteriologist, helped make penicillin. So maybe it's in the family.
Could be.
But also, I just had the opportunity to go after which I wanted. So I grew up in the country. There was nothing to do. There was no place to go except play with toys and build stuff and walk around in the woods and dig up fossils in the yard. And so become a scientist as quick as you can.
Get out and move on.
Yeah. So by 4th grade, I was already the science nerd in my school. So.
All right, so I think we're kind of running out of questions. I want a final thought here. Here we are on 32 years birthday of Hubble coming up. What do we predict when we come back here in 32 years? What are we going to say about Webb? You start.
I don't have a clue, and I will say why I don't have a clue. When the night before we launched to deploy Hubble, we were foolish enough to sit around and guess what were going to be some of the discoveries from Hubble, and we found subsequently we didn't have a clue.
You got anything?
I think I'm with him. The thing that will excite me the most is that we do not have a clue about the real surprise out there. But on the other hand, it's also true that Hubble was there already.
Yeah.
So they found a lot of the big surprises. There were huge things that just people did not expect at all. And so we're not quite as young as we were.
And we don't explore for things we know.
Yeah.
So Hubble got all the good surprises, huh?
Well, they got, maybe they got the good ones.
We still got dark matter coming.
Yeah.
France, what do you think? What will we say?
Well, this is also, today is I think it's the anniversary of Einstein's passing in 1955. And I mean, there was I just have tremendous confidence in the human spirit, in the drive to know and to understand. And I think 32 years from now, we'll have the, where's Matt Malkin? We'll have those 2 big ground-based telescopes, and we'll have a lot of space-based telescopes up there. And I mean, Einstein upended our understanding in a whole, just completely revolutionary way. And I think that this telescope will do the same, and we'll have had time to make many more discoveries. So.
All right, we'll see you in 32 years. France, John, Charlie, you have taken cosmetology to new levels. Thank you. It's a great pleasure.
Thank you.
So what an incredible, just over an hour and 15 minutes set of stories, which is, I was just sitting reflecting that tonight's conversation reflects so much of what we tried to do at AIP, which is both tell the story and preserve the history of the physical sciences while we look forward at making advances in discovery and wonder and really trying to bring about not just new discovery, but also cultivating the next generation of scientists. And these stories are so important in that effort. So I want to thank on your behalf our panelists, our trustees who joined us this evening. You get a glimpse of the honor that we feel when we have our board come together, that we get to engage in conversations like this at the board table around the future of our work here at AIP and AIP Foundation. So thank you to France and to John and to Charlie for this evening, but also special thanks to Miles for taking time to come today. So thank you. And thank you again for coming and joining us this evening. Most importantly, thank you for your support for AIP. This is going to be just the first of future convenings that we'll bring together our donor community and our supporters and our friends across the community here in Washington and further afield. So thank you so much for joining us, and look forward to the next event.